right, scholars, welcome back. All right, you survived, you did it, you're here, right? All right, so hope everyone enjoyed their spring break. I enjoyed it as best I could. Just went around and just enjoyed myself really. Got caught up on a good amount of work. It's always something that can be done. So welcome back to the second half, right? Let me see. No real announcements. We're just kind of continuing where we left off, continuing with chapter 3. Remember, for the semester, we're trying to get through chapter 4. So that means exam 2 will cover chapters 3 and 4. We're going to wrap up chapter 3 this week on Wednesday. Yeah. And, so far the whole semester, we've really just been focused on differentiation. So I think like initially we introduced differentiation, and we may have had like the limit definition of the difference quotient. And like, if again, the best way I can sum up derivative, give me just a moment. Okay. So the best way I can sum up the, again, it's just the slope of the tangent line at a point, right? And like if we manually try to find a derivative, because there's like wiggle room, you can't get it exact manually, So that's why we had the limit definition, but then we explored, shortcuts, right? So that limit definition, when you're trying to find a derivative, it might take up the whole page or whatever. But then once you start invoking like some of the techniques, the differentiation techniques and shortcuts that we have, that whole page worth of work gets condensed down into like one line. All right. So we've been exploring that. I think with this chapter, we've been exploring like some applications of the derivative, just some different ways that it's used, like especially like with the first derivative test, second derivative test, where the first derivative tells us whether the original function is increasing or decreasing. The second derivative tells us whether the original function is concave up and concave down. And then using those two tests, we can find like the relative max and the relative min, and incorporate that into our curve sketching. Right? Let me get this straight. Okay. So we talked about how to incorporate the first test again, where the first derivative tells us increasing or decreasing. Second derivative tells us whether the original function is concave up or concave down. It also identifies our points of inflection. And so we were coupling those tests with a few other techniques to curve sketch. I think, so again, this week we're going to be wrapping up chapter 3. We'll see how quickly we get through this section. Okay. So chapter 3 are applications of differentiation. And we're going to be working on section 3.7, elasticity of demand, right? A few objectives here. One, find the elasticity of a demand function, find the maximum of a total revenue function, and characterize demand in terms of elasticity. So the elasticity of demand, E, is given as a function price X by this guy here. So the elasticity of demand is going to be the negative. Let me see. We have X times D prime of X over dx. Where is D? So that's the demand function, right? So given a demand function, the elasticity of that demand function is given by this, X times D prime over D. Okay. So let me see. So we have this theorem 11. Total revenue is increasing at those X values for which the elasticity is less than 1. So let me see. So when the elasticity is less than 1, the total revenue is increasing. When the elasticity is greater than 1, the total revenue is decreasing at those values of X. And the total revenue is maximized at the values of X for which the elasticity is equal to 1. Okay, so it does make sense that we want to maximize the revenue. Like if the revenue is increasing, that means that we're not getting the most bang for our buck. We're not, it's not maximized, right? If the total revenue is decreasing, well, obviously you don't want the revenue to decrease, right? So oftentimes it seems like you would want the revenue to be maximized, so you would want your elasticity of demand to equal 1. That's just me kind of piggybacking off of this slide. So let's see what we have here. All right, so elasticity of demand for video game rentals. The demand for video game rentals at Clicks Video Games is given by this function here, where Q is the number of video games rented per day at X dollars per rental. Let's see. Okay, so that's our demand function. Find the elasticity of the demand as a function of x. Find the elasticity when x is 2 and when x is 5. Interpret the meaning of these values of the elasticity and find the value of x for which the elasticity is equal to 1. What is the significance of this price? Okay, so we kind of let's find the elasticity. I need a blank page. So let's check. This is slide 7. Copy and paste. All right, and then this we're gonna assume that this is charged enough for now. Okay, so let's go like this. A moment ago, we just said the elasticity of demand. We said it was x time. I think it was a negative d prime of x over d of x. Let me confirm that. The negative x d prime. Okay, so that's correct. And then we need this demand function just given 120 minus 20x. Let's get a copy of that guy. I'm gonna paste it right there. So then we're asked to find the elasticity of this demand function. So let's give it a go. Let's go ahead and find d prime. I think I'm gonna move this guy. So let's find our d prime. Looks like it's just negative 20 because the derivative of the first term, the derivative of a constant is 0. The derivative of negative 20x is just negative 20. Okay. So then let's put all these pieces together. So then the elasticity of the demand function look like it's going to be negative x times d prime over d, which is this. Okay. So that's what we got for part A. Find the elasticity as a function of x. That's what we got. Let's highlight this guy. And as usual, if you have questions or if anything isn't clear, feel free to unmute yourself to get my attention and we can talk about it. Hopefully you all have been finding your way. Keep in mind that I'm available for like office hours. My office hours are what? Tuesdays and Thursdays from 9 to 11 via Zoom. The best way is like if you intend to attend office hours, just show up and send me a quick text on my office cell phone number so that I can like open up that window. Otherwise, I might not notice it. So that's why the best way to reach me or to get my attention is a text message via my office cell phone number. You know, and you know, if my explanation isn't, you know, if you don't resonate with that, then hopefully you either work with a classmate or you found a tutor. I think it's like crucial for information like this, right? Okay, so this is our elasticity. Actually, let's simplify this. So we get a double negative. So that top simplifies down. Like, can we simplify a little bit more? I feel like we can take it a little bit further. What if we factor out 20x? Will that help us? Not really. Looks like we could factor out 20 though. Let's simplify this guy. I think we can simplify it down. So it looks like we can factor out 20 from all terms, right? So let's see. This is going to be, I'm thinking it's going to be 20 over 20. On top, it looks like we're going to be left with x. On bottom, is that a 6? 6 minus x, then x. All right. So just for the sake of space, I think this is what we get. And redo that as well. So after we simplify it, we got something like this. Okay. All right, so that's part A. Find the elasticity when x is 2 and 5 and then interpret the results. Come on. So then for part B, the elasticity when x is 2, that's going to be 6 minus 2 under 2. 6 minus 2 is a 4, so what is that, a half? Notice, okay, give me a second, because I saw that always kind of distracts me. Let's go settings right here. It'd be like if I had control over that. I want to know when you guys join, but I don't want to know when you leave, because when you leave, it distracts me, and then I'm like, that's why I had that off to begin with. But it's okay. We're all adults, right? I treat you like adult. You're responsible, right? So I make sure to do on my end to make myself available for you all as best I can. Try to make the information as clear as I can, um, and give you like a million attempts to get through this stuff. But if you feel like I totally understand about listening to somebody else talk about this. That could be kind of. But then I know that sometimes students are just changing devices too. So I never really know. So I just like do what I need to do so that I can focus and keep my rhythm and flow. Let's see. All right. So notice that the elasticity is less than 1. So that implies if when x is 2, what do we say? I think the revenue is increasing. I think that's what we said. If the elasticity is less than 1, the total revenue is increasing. So that implies that the total revenue is increasing when, I'm going to just do this instead, when x is equal to 2. Okay. Let's find the elasticity of demand when x is 5. So that's going to be 6 minus 5 under 5, which is just 5. Notice that that's larger than 1. So that implies that the total, matter of fact, what I'm going to do, because I can, I'm just going to copy and paste, and make my augmentations, right? Like for instance, this guy needs to be inverted. I guess that'll suffice. It looks weird, but the total revenue is decreasing when x is what, 5, because the elasticity is larger than 1. Okay, so we got this result for that one. We got this result for that one. And like another thing about like the structure of this course, because we're remote, I'm not really trying to have you guys commit this memory. I'm just trying to expose you to the information and get you through integration. I just want you to have to do the best that you can, right? And trying to help you all get through it. This isn't like rigorous where you're like in a testing environment with just a paper and pencil and calculator, right? My intent is really to expose you to the information so that you're aware of it. So that way, like when you go beyond this course, it's not foreign. You would have seen the things that you need to have seen and been exposed to it, and you can use those experiences to keep moving forward. Right? Okay. I think we got that part. And then find the value for which the elasticity is 1. So that's the max. That's to maximize the total revenue. Maybe we can fit that here. We want the elasticity. We want E of x to equal 1, which is this 6 minus x under x. We want that to equal 1. Okay. I am tempted to set it to 0. Right? So if we subtract 1, we're going to be subtracting 6 minus x. So on top, we're going to have x minus 6 plus x over 6 minus x equals 0, right? So all I subtracted 1 on both sides. I had my elasticity minus 1. Then 1 is going to be the same as 6 minus x over 6 minus x. Then, basically adding fractions, right? Okay. So then, now this guy is only going to be equal to 0 when the numerator is 0, right? So we have this 2x minus 6. Let me see, add and divide. It looks like when x is 3, right? X equals 3 look like it makes that 0. Yeah, right? Again, a fraction is only going to be 0 when the numerator is 0. Okay. So we're saying that when x is 3, it maximizes the revenue, right? So we got that when x is 3. The total revenue is maximized. Let me see. So x is the dollars per rental. So what we're saying that if we rent out our video games at $2 a rental, then the total revenue is increasing. If we rent out our video games at $5 per rental, the total revenue is decreasing. I think that, like, based on their data, the 5 might be too much if people don't want to pay that much for it. So then fewer people are going to buy it, decreasing our total overall revenue, right? So then, according to that demand function, the elasticity is maximized if we rent our video games at $3 a pop. Now, that kind of takes me to spring break. I don't know if I've shared this with y'all or not, because my days, everything is running together. But one of the things I did, I actually did something for the first time. I did a lot of first, actually. I did like the escape room. Now, personally, I felt like it was overpriced, right? They charged like $40 a person, so it was just two of us. Two of us was like $80 odd dollars plus tax. I was like, man, this is a bit much, but I was glad I did it. I had a good time. I felt like I was on The Amazing Race, which is like one of my favorite shows. I literally was watching that right before class started. Well, before I started my match before class started. But anyway, I felt like it was overpriced. So usually with that experience like that, I encourage people, if you've never done it, I think it's a good idea to do it at least once. But to me, I felt like it was overpriced. I felt like a more reasonable price for something like that may have been $25, but then maybe they can't afford it, So they might need me to hire me to come in and do an analysis so that they can maximize their total revenue and get the most bang for the buck. Because if they overcharge, people are not going to want to come back. But if they charge too little, then they're selling themselves short. You see what I'm saying? Like, it's kind of fun. So then from there, I started to sign up for this like VR, you put on these little sensors or whatever, but I passed on it. But then another day I went and sampled, I did a demo of the Apple Vision Pro. That was a lot of fun. Like, I had that vision like eons ago when I first experienced VR. But then with the Apple Vision Pro, I was like, with the VR, I was like, well, okay, it's cool, but you can't see your surroundings. Then I discovered AR, which is augmented reality. I was like, oh, well, why don't they make goggles that are augmented reality? Thus, here, insert Apple Vision Pro. And so I tried it, man. It was surreal. I had so much fun. I was only using it for maybe like 10 or 15 minutes. So at some point, whenever I get a chance, I am going to get my hands on it. But that's neither here nor there. Okay, so now Apple, man, they are doing some crazy stuff. $3,500. People are like willing to pay it, man. I was like, man, that just seems surreal, right? Okay, let's see, how do we do? Okay, so our D prime was -20, so our elasticity was X over 6 minus X. We got that. When X is 2, the elasticity was half, is less than 1. Thus, a small percentage increase in price will cause an even smaller percentage decrease in the quantity demanded. Since the demand is inelastic, raising the price of each rental by a small amount will increase the total revenue, right? So that's essentially what we were saying. The total revenue is increasing, so we haven't maximized the rental price. But if we rent them at $5 a rental, the elasticity is greater than 1. Thus, a small percentage increase in the price will cause a larger percentage decrease in the demand. Since the demand is elastic, raising the price of each rental by a small amount will decrease the total revenue, right? So that's still not maximized. And then here it's going to be maximized. So we set the elasticity equal to 1. We got when X was 3. So this is the price that results in unit elasticity at $3 per rental will maximize the total revenue. So you plug that into your demand function to get the total revenue of $180 per day. Okay, that's interesting. We're already halfway through this guy. Now that's a quick check. I'll leave that as an exercise for you. I guess I didn't realize that I'm like that non-talkative when I'm not with you all, because like as soon as I start teaching, like my mouth just gets dry out of nowhere. But it only happens like when I'm teaching, I guess, because I have to talk, And I got my wood over here. We're almost actually done with this. Wow, this is going to be it. But I'm going to pull up some other stuff that we can work on. Let's see. So elasticity of the demand. Wayne's Honey Farm sells honey-based moisturizing cream for $12 per jar. This is interesting. Sorry, I have to tell this story. So a friend of mine sent me this video this morning about the benefits of honey and like what's the best honey to use and how to use it. And one of the properties was that you can use honey as a topical cream to like treat like burns, and like it has all these like health benefits because the bees are getting the pollen from like all of these flowers, and the flowers soak up a lot of like sunlight and all this nutrients from the sun, so it gets transferred from the sun into the honey, and then when you eat it and use it, it goes into you. So it has just like a lot of like health benefits, but surprisingly, that's what they were saying, is that it can be used as a topical cream for skincare and just, you know. So anyway, it was an interesting little short or whatever video. Wayne's Honey Farm sells honey-based moisturizing cream for $12 a jar. At this price, it sells 14,500 jars per month. To see if the price is too high or too low, Wayne's Honey Farm raised the price to $18 per jar. At this price, it sells this many jars per month. Use the exponential demand function, this guy, to find the following. We're asked to find the elasticity, and then find the price at which Wayne's Honey Farm should sell the jars of moisturizer cream for the demand to have unit elasticity. Also give the resulting total monthly revenue. So same thing, right? Just with a different function. Same thing like we did in the last example, just with a slightly more challenging function. Let me get a copy of this other one. I have one at the end. This is slide 19. Copy. Paste. Okay. So let me get a copy of this demand function. 26,380.746 e to the negative 0.04987 x. Okay. 26,380.746 e to the negative 0.04987 x. Okay. Cut. Paste. All right. So if that's our demand function, so then part A asks us to find our elasticity of demand. And real quick, so our elasticity of demand, I think it's negative x times d prime of x over d of x. Okay. Oh, so if that's our d, so then d prime, let's go ahead and find that. So the derivative of e is itself times the derivative of the power. So that's going to be 26,380.746 e to the negative 0.04987 x times the derivative of the power is this negative 4987. Okay. So that's our d prime. I'm going to leave it like that for now. So then our elasticity is going to take on the form negative x d prime. So times this negative 4987 times this 26,380.746 times e to the negative 0.04987x, okay? Divided by, now we could crunch that number. I'm just leaving it like this just because. Divided by d of x, which is this 26,380.746 e to the negative 0.04987x. Okay. It looks like we have some cancellations going on. Am I missing something? Yeah, I think it looks like it's like this cancels all of this, and we're left with that. It looks like our elasticity of demand 0.04987x. Okay. So we're working on part B. So then part B, we want to maximize the total revenue, right? So we want to find out what value of X makes the elasticity equal to 1. So then X is going to be 1 divided by that number. Siri, what's 1 divided by 0.04987?
1 divided by 0.04987 is approximately 20.0521.
So $20.05. That's a reasonable result for some honey, some cream, honey-based topical cream or whatever. I feel good about this, so I'm going to go forward. Okay, let me see. Negative X times D prime over D. So I think we got that same elasticity. $20.05. Let's see. Come on. There we go. $20.05. Wayne's Honey Farm should sell its jars for $20.05 a jar. This would maximize the revenue. The month. Oh, we forgot the total monthly revenue generated. So we will plug that X into the demand function. Well, I just forgot to do it. Wow, in a month, almost $200,000 a month, based on that demand function. Okay. Muy interesante. Okay. And then we have a summary of this section with the elasticity of demand. Again, we say the demand is inelastic when the elasticity is less than 1, and that means the total revenue is decreased. And then that means the total revenue is decreasing. Wait a minute. Maybe that means it's increasing. Sorry, yeah, that means it's increasing. And then when the elasticity is larger than 1, the total revenue is decreasing. So we reach unity elasticity when the elasticity is equal to 1, and that's going to maximize our total revenue. Okay. Okay. So let me think. Let me add a page like this. Okay. And what I'm going to do is hop over to Pearson and let's work some assignments, some questions from the section. Get my device to work properly. Let's just go full screen for now. Hello? Sign in. Hello. Calculus for business. Okay, so all of this is here. And again, you said everything that you see here you can still access. You get unlimited attempts on everything. There should only be a 5% late penalty on all assignments. So even your exam, like if your exam is less than 95%, you're welcome to attempt it again. And the system is only going to show you whatever your highest score is. So you have nothing to lose and everything to gain. If you wanted to go back and work on things to get them up to 95%, if you are going back and working on old assignments, I would prioritize exams first. That's where you're going to get the most bang for your buck. Then once your exams are where you want them to be, then I would prioritize the quizzes because that's less work for more weight. And then if you just feel up to it, you can go back to the homework. And this is at any time. The elasticity of demand is 3.7. Week 10. Elasticity of demand. Maybe I think we might be able to get through all of this. So we're just going to start with the first question. Use the quotient rule to find a derivative. Can that be factored? No, it doesn't look like they cancel. Okay. I kind of want to skip this one, but let me just get a copy. This is like a review question, but I mean, I think we have time. I'm just being lazy. Like, I definitely struggle with like senior artists. That never stopped. Like, even when I was a student at Morehouse, and then every time we get close to like a holiday after spring break, I struggle. I just be like, man, I don't want to do any of this. Copy. Let's go. Ugh. Nope. Let's try this again. There we go. Finally, let's cut that, and let's change our view. Seamless. All right. Where is the page break? I can't see the page break. There it is. Okay. All right, so I'll just use it as a reference. Well, I guess I can. Man, my device is like, it does not want to respond. It's kind of struggling a bit. Okay. So quotient rule, right? This should be a review. So we'll say dy by dx. So quotient rule is low d high minus high d low over low low. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. Oh. Okay, let's expand it out. What is that? 2x cubed minus 6x squared is that plus 14x 42 minus, so negative 2x cubed plus 12x squared minus 2x. Over. I'm gonna leave this like this. Negative 2x cubed cancels this guy. Okay. 12 minus 6 is going to be 6x squared. So we used that one, we used that one. 14 minus 2 is 12. And we use that one and that one. So the only one that's left is then minus 42. 3642. Looks like we can factor out a 6 from all of those terms. If we factor out 6, we have what? X squared plus 2x minus 7. X squared plus 7 squared. I was kind of hoping we can factor, but it doesn't look like we can factor it. Because we will be looking for two numbers that multiply to give us -7 and add to give us 2. And the only factors of -7 are 1 and 7. And you can't add those to get to 2. So I think one of these two forms should work. Okay. So settings, turn this off. I might have to zoom out. All right. Yeah, I'm not getting anything to cancel. So on top, we got this 6x squared plus 12x minus 42. On bottom, x squared plus 7. Let's see. X squared plus 7 quantity squared. All right, let's see if this works. Okay, let's go on to the next question. Differentiate. Okay. So this is question 2. This comes from section 1.7, question 32. Differentiate. We got f of x equals, we got this 8 minus x over 1 plus x, like that. So it looks like we have to do the chain rule. The outside function, so the 1/2 comes down. Subtract 1 from the power because it's a -1/2. Times the derivative inside function. Looks like we got to use the quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom is just 1 all over the bottom squared. Okay. Let's see, what can we, okay. So this is going to be the same as now. We have this half. If I flip, I'm going to have 1 plus x to the power of a half over 8 minus x to the power of a half. Okay. Then I want to say times. Now, if we simplify that guy, we got a, it looks like we have a -1 minus x minus 8 plus x over 1 plus x squared. Okay. It looks like this is canceled by this. Looks like we had a -9 on top. Okay, we got we got some cancellations going on here. So on bottom, we have this 2, 8 minus x to the 1/2, and we have this 1 plus x squared. And then on top, looks like we have this 1 plus x to the 1/2, and I think we have a -9. Okay. So then we can subtract those powers. We can say a half minus 2 is a -3/2. Okay. So essentially, this is going to be gone, and this is going to turn into 3/2. And I think that's as far as we can take it. So let's try that. Let me write the final result. So we're getting on bottom, we have this 2 times, we got this 8 minus x to the 1/2. Let me think. Will it help us to combine those? I mean, we could go a little further. Because that's the same as x to the half, or the thing to the half, to and plus or times to the power of 1. We can combine those. Let me kind of do a little bit more simplification. So that denominator, we have 2, 8 minus x to the 1/2. And then I'm going to do this 1 plus x to the 1/2. And then I'm going to leave this guy as 1 plus x, right? Because I'm going to put those two together and, to see how that affects it. So then we can move those into the same radical. That doesn't seem like it's making anything better because we would have to FOIL and we get a whole nother expression. So I'm just going to go with what I had before. It's not really, nothing's canceling or anything. So I'm going to go with this result here. Let me see. We got this 2, 8 minus x to the 1/2, 1 plus x to the 3/2 under a -9. All right, let's see. I feel like, we really only know if we just try. So we're going to try. Oh, come on. Okay, there we go. Let's go fraction. Now on top we have -9. And another thing we could do, we can look at the viewing example before we submit ours and see if they have a similar form. But I'm just going to go with this. 8 minus x to the power. If that's, let's say the square root, right? Square root of 8 minus x. And then here, square root. We got 1 plus x cubed. Yeah, I feel like we could probably go a little further. Man, that's so weird. Okay. Well, we got it. Let's go on to the next question. Okay, let's give this one a go. So this is what question, I think this is question 3. So this comes from section 2.3, question 7. Again, we're asked to differentiate. We got f of x equals x to the 4 times the natural log of 9x. So we're just taking a derivative. So it looks like we got to use the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. All right. So the first, which is just this guy, the derivative of natural log, I think is du over u. So that's going to be 9 over 9x. That's the first times the derivative of the second plus the second times the derivative of the first, which is 4x cubed. And we can simplify. These 9s cancel. This turns this into a 3. So it looks like all of that's gone. We have x cubed. We could factor out the x cubed. If we factor out x cubed, in that first term, it looks like we're left with a 1. And the second term, looks like we have 4 times the natural log of 9x. So we got x to the power of 3 times 1 plus 4 times the natural log of 9x. Right. Determine the vertical asymptotes of the function if none exists. So natural log. Okay. So in general, for the log, the inside part, the x squared plus 4 has to be strictly greater than 0. So I'm just finding the domain of this guy. All right, this is question 4. Find the vertical asymptote. We have this f of x equals the natural log of x squared plus 4. Okay. So again, if we're finding the domain of the log, this x squared plus 4 has to be strictly greater than 0. So let's see what happens when we solve this. Subtract. We get x squared is greater than a negative 4. That's always, let me see. Log function. So when is that above 0? Like, okay. For instance, when I'm looking at this line here, we have a quadratic that's been moved up by 4. When is that positive? Well, it's always positive. It never crosses the x-axis, and it's always above the x-axis. So something like this tells me that that line and says to me that the domain is all reals. Like try to plug a negative into the original because graph is probably like a little like a wing shape or something. Let's look at the graph before we submit this. But it seems like the domain is all reals, right? That's the impression that I get. Again, when is something squared greater than negative? Well, always, right? So that also confirms that the domain is all reals. Before we submit it, I want to look at the graph. Okay, just to confirm our notion. Okay, so we're going to go to y equals, we have the natural log of x squared plus 4. Yeah, and I'm thinking like some kind of like a wing V-shape kind of thing. It's like they go in opposite directions because like when x is positive, I think it behaves like a log, but then when x is negative, it's like inverted or something. It's going to do something funky. Let's see what happens if we just look at the graph. Yeah, see, like that's the wing shape that I was, because it was almost behaving like a log, but then so that confirms. That's interesting. That confirms that the domain is we can go with all reals in that case. Okay. So here, let's just minimize this a little. When x is 0, I don't think there are no vertical asymptotes. Whatever reason my device is like not responding to my touch. Yeah, okay, so we're good. Let's go on to the next question. For this demand function, find the elasticity. Find the elasticity when P is 88. And this, let me see. Inelastic. I think inelastic was the first one. When I got to look back at the notes. It's actually up here. Let me look at it real quick. So inelastic, way back at the beginning, back in the before time, when life was simple. I can't finish that story. Okay, let me see. It doesn't say it there, but I saw it somewhere right here. Let's look here. So the elasticity is less than 1. So when it's less than 1, that means it's inelastic. Okay, so less than 1 means inelastic, and then you can take it from there. Okay. All right. So this should be question 5. This is fine. I have what I need. So question 5, this comes from section 3.7, question number 1. So our demand function, we got 442 minus P, okay? Let's find D prime. Looks like it's -1. So then the elasticity of the function based on P, again, that's going to be -P times D prime over D. So that's going to be -P. Now D prime is -1. And D is this 442 minus P. Okay. So it looks like our elasticity of demand is going to be this 442 minus P under P. Okay. Let's kind of, come on. Let's go about it in the middle, actually. So find the equation for the elasticity. So we got P over 442 minus P. Come on. Sorry, I think my device is tired. It has a full charge, but for whatever reason, it's just like not being responsive. Okay. We got time for like a couple more. Let me see. So then P over 442 minus P. Find the elasticity when P is 88. It was almost there. Here we go. Okay. So we're getting 88 divided by 442. 442 minus 88. That looks like it's less than 1, right? So we get 2486. 2486. 2486. Okay. So notice that that's less than 1, right? And for whatever reason, I'm not remembering. Let me just go back to that example right here. That's a quick check. Okay. Because it's less than 1 means it's inelastic. Ours is less than 1, so that means that it's inelastic, which means the total revenue. Shit. I'm sorry. I don't know. It's just not sticking in my mind for whatever reason. All right. Okay. So the total revenue is increasing. Okay. I guess one way you can kind of think of it is like if we're trying to get to 1, so if the elasticity is less than 1, we need to increase to get to 1. So you can say the total revenue is increasing. If you're larger than 1, and you're still trying to get to 1, so the total revenue you need to decrease to get to 1. So that's how I'm going to remember that. All right. That's kind of how what you got to do with like some of this information is just think of like weird ways to remember it. At least that's what I used to do. I haven't really done that in a while. Type in integer or fraction. Okay. Come on. So let's hit math as a fraction. 44 over 177. 44 over 177. Okay. It's less than 1, so that means inelastic. So we want to maximize this. So that's when the elasticity is equal to 1. So if we set the elasticity, we set it equal to 1 and solve. So if I subtract 1, let me see, on top, I'm going to have minus 442 plus P over 442 minus P. Okay, that's equal to 0. So then what value of P is going to make this 0? We just said the numerator is 0. We have 2P minus 442. So then P equals 442 over 2, which is 221. It's $221. 221. That's interesting. Sorry, my device is like. How do they used to get out of that? Okay, that'll work. I think we got a 221. Okay, so we're essentially out of time. Are there any burning questions before we go our separate ways to the ones that we're talking about elasticity of demand? But that's okay. Let me go ahead and make a copy of this available. I like to share. I'm going to send this to Box. Let's put it in the proper folder. 24. Traditional, yes. Let me see.
Hello.
Yes.
I got a question. So for the question one, I mean example one, I was wondering how did you get 6 minus X on the bottom part?
Right, hang on. So part 1. Let's see. Quick check. 6 minus X for part A. Is that correct? I think you might be muted. All right. So we had our demand function, right? We went on to find a derivative, which was just happened to be negative 20. So we got lucky that it was simple. So then elasticity, we use this formula, negative X times D prime over D. So here's our negative X, here's our D prime, and here's our D. So then I noticed that all of these numbers were a multiple of 20. So double negative, those became positive. If you factor out 20 from all factors and then cancel the 20s, you get this.
Oh, okay.
Are there any other questions before we go our separate ways? We still got a good amount, like maybe about 15 minutes if you guys want to ask questions. Going once, going twice. Okay. Okay, so I think I made a copy of this available. If there aren't any burning questions, sorry, I'm just trying to get to the bottom. If there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, take care. And we'll on Wednesday we'll be wrapping up chapter 3. Looks like I think it's going to be implicit differentiation. So again, anything that I'm gonna say live is already in my recording, so you are welcome to use those recordings to get ahead, and then that way we can use class as a review. It's the same material, same delivery. All right, gentlemen, enjoy your evening and see you next time. Take care. Peace. How's your music going? I always want to